Thanks. Good morning. All right, so our last topic on graphs is what we're going to cover this morning. In some ways, this is more for your fuller understanding of how to solve some of these problems. What we're going to talk about today, you could solve in alternative ways than the method I'm going to describe, but you're going to see that you get a little bit of benefits by using these algorithms that we discussed this morning. So, all right, the first problem is called a transitive closure problem. You guys know what a transitive closure is? You remember from Comp 1210? What's a transitive closure of a relation? Transitivity. All right. So let's do some definitions here. So if you remember, a relation R is transitive if given X R Y and Y R Z, then it implies that X R Z. So, for example, less than or equal to is an example of a transitive relation. Now, the transitive closure of a relation, I should say, so it's transitive closure of a relation, and I guess it's relative to a member of the universal set. Let's say this one 4. Right, so the transitive closure is a set of all the things that some element is related to. Just as a very simple example, if you're talking about if the relation was less than or equal to, we're talking about all integers. Then you could say, for example, 3 is less than or equal to 4. 4 is less than or equal to 5. By transitivity, 3 will be less than or equal to 5. And the transitive closure of 3 under the less than or equal to operator will basically be all integers greater than or equal to 3. All right? The transitive closure is the whole set. Now, the problem that we want to calculate or compute is given a set of relations. So you usually might be given a bunch of elements within some finite universe. And there are relations that are naturally defined. For example, it might be adjacent. The entities might be countries that are connected by a land, countries, and then there's a relation between them if they're connected by a land border, for example. So you might have adjacent countries. Those would be your relations. And what the transitive closure in that context might represent is where could you travel to via only land from any given country? You understand the question? What I'm saying? If I were to ask you to calculate from any given country, what are all the other countries you could reach if you only had some kind of land conveying vehicle, whether a car, train, or bicycle, or whatever, where could you reach? I'd be asking a transitive closure question, right? And in that context, I hope you realize that it essentially is a graph question, right? You're using the graph to represent the entities and their relations between them, and asking for the transitive closure is really asking what are all the reachable nodes from some given start point, where the edge defines what the relation is for a single pair. Somebody's mic is on. Or not. So the problem, the transitive closure problem for us anyway, right. So a common example of where this might occur is this is often, so you know paint programs. So you might have a drawing and there are lines, you know, the lines define the boundary, and then you want to paint the inside, the interior of that boundary with a color, right? So you know about flood fill. You've heard of that operation? You guys never use a paint program, even when you're like 5 years old. It's just called it what? Exactly. You call the operation is often named fill. Exactly. Sorry? Bucket fill, sometimes you see that. But in general, all you're doing is you're gonna color all the pixels that are interior to some boundary. So the one that the user clicks on, what you want to do is assign it the color that they've chosen, and then all its neighbors that same color, and all its neighbors that same color. Where do you stop? It's when 2 pixels are no longer, they have one of the boundaries between them. So you can imagine that in that scenario, you have a relation between pixels if there is a boundary between them. But originally, you only know where the boundary is. You don't necessarily know whether inside is connected to outside, right? So if you wanted to implement the paint fill operation, and you wanted to know which pixels are supposed to get the color that you just assigned, especially if you want this to be undoable, you kind of want to calculate pixels up front rather than just change the pixels, and then when the user says, oops, that's not what I want, you say, well, too bad. I done set the pixels already, and I didn't remember what they used to be. So you might want to do that calculation beforehand. How do you do that? How could you represent that as a transitive closure problem? You could So here's my boundary. And if I want to color some point inside, I need to know that that color must spread only to the interior, but not out here. So any pixel out there, outside of that boundary, should be unaffected. So how can I know which pixels are supposed to be affected? When I examine where that boundary is, I will only know relative to the boundary which pixels are adjacent to it, but I won't necessarily know. So when the user clicks in here, I won't know at that point in time whether this pixel and this pixel are on the same side of that boundary. I'll certainly know whether it is on the same side of the ones next to it. I could figure that out immediately. But to find out for those pixels that are far away, or even the other ones that are far away on the interior, that's going to take some steps. So one approach is I could define a graph. And two pixels would be neighbors if they're immediately adjacent to each other and they're the same color, right? In that case, the boundary would end up separating nodes, which are pixels, so that the pixels inside would not be neighbors, or the pixels outside would not be neighbors of the pixels inside. Because when you look at the adjacent pixels, they're going to have a boundary pixel between them. And then what you do is, so that would create a graph. Pixels will be related to each other if they're adjacent to each other with the same color. At that point, though, you don't really have notions of interior versus exterior. The next step is compute the transitive closure. Which node do you want the transitive closure of? It's the one that the user clicks on. That set of pixels that are in that transitive closure will be the ones that need to be assigned that color that you've just selected. Okay? So that's an example of when you'd want to use it. Okay, so enough for the motivation. How do we actually go about solving this? Now, if you recall, for those of you who actually go to tutorial, and then the subset of you who then pay attention, and then the subset of you who actually grasped what was going on. Did I just reduce that subset to one person? who then grasped what was going on? If you remember that discussion about what's the meaning of the square of the adjacency matrix? Remember that discussion? When you take that adjacency matrix of a graph and you square it, right? What we said was you get values that represent the number of paths that are exactly 2 hops between pairs of nodes. And if you're to cube it, you'd get a number of paths that are 3 hops, and so on. All right. So here's one approach. We could take that approach because in this case, we just want to know, is it possible to get there? We don't really care how many ways there are to get there. So we could have, the original adjacency matrix is essentially binary. It's all zeros and ones. I could have, instead of putting numbers in there, so in other words, when I take my product, instead of writing down 2 if there are 2 paths, just still write down 1 to represent it is possible that they're connected. Because what I really want is, given any two values, this x is 1 pixel and y is some other pixel, I want a yes or a no answer. Is the other pixel in the transitive closure of the first one? It's just a yes or no. It could be a million different paths. I don't care. There is a path. That's what I care about. Yes? So then, if I'm focused on just that binary decision, are they related or not? Then I can work with a slightly simpler form of the power of that matrix. It doesn't have to actually be the literal power of the matrix. What I could do is contemplate, instead of using normal matrix multiplication, swap out the following operations. Where I used to do multiplication, I'll do a logical AND. And where I used to do addition, I'll do a logical OR. What's the value of that? If you remember the discussion in the tutorial about why the meaning of the entries in the squared matrix is the number of paths that take exactly 2 hops. You remember that when you take an entry in the row, let's say you're taking I to j, and there's a 1 in there. When you dot product with the matrix on the right, and you're looking at entry jk, that means you can go from j to k, and there's a 1 in there. Remember that what happened there was that you got those 2 1s coincided because there was a path from I to j and a path from j to k in that context. And so that logical and just simply allows that 1 to be 1. Now, of course, 1 times 1 is also 1, so the product is not different in that case. Product of numbers that are either 0 or 1 is the same as the logical and of numbers that are either 0 or 1. But when it comes to now taking the full dot product, we would have been taking these products of corresponding entries in the two vectors, and then normally we'd add them together. And that's how you might get 2 paths, 3 paths, 4, whatever. But now instead of doing a sum, we're going to do an OR. So that means that if you even have just 1 pair for which both was possible in others, 1 j for which you could go from I to j and from j to k, then that immediately means you could go from I to k. So at that point, instead of doing an actual plus in our dot product, we change it to an OR. And then we would produce a binary matrix. And that matrix would tell us, is it possible to go from each entry ij would tell us, is it possible to go from I to j in 2 steps? And the answer is, if it's a 1, it means the answer is yes. If it's a 0, that means the answer is no. It's not going to tell us a number of ways, it's just going to tell us whether it's possible. So this is, let's call this method solution. Let me set the problem up. We're given a graph. I said that. Let me set up, because all of them are going to depend on this. So the problem is we're given a graph G. This is an undirected graph. So we're going to do this for all nodes. So let A represent the adjacency matrix of G. So method 1, we could compute. It's based on the idea of powers of the matrix of the adjacency matrix, but this is going to be a kind of pseudo multiplication. So that what used to be multiplication now becomes logical and what used to be addition now becomes a logical OR. Okay, so now the meaning of the entry in, so now entry Aij in some power k of that adjacency matrix represents, is it going to be equal to 1 if there's a path from I to j in k steps. So let me call it a k path. K length path. It's not even, yes. And a 0 otherwise. Now, if you recall from the tutorial, what we had to do with those powers of matrices, each one is telling us whether there is a k-length path. If I just want to know, is there a path, regardless of how long, we had a discussion on this. What's the maximum length you might need to compute? The number of nodes, because these are simple paths. Simple paths don't repeat nodes. So if you want to know if it came from I to j, then the most number of nodes you'd have to go through is 1 less than the number of nodes. So the highest power you need is n-1, where n is the number of nodes. But remember what you would have had to have done in the old case, because now you want any length, you have to sum all those different powers. But now what we can do is compute logical OR of these different powers. So now we'll compute I or A or A squared or A cubed or all the way up to A to the n-1. The logical ORs. And of course, at that point, that would be the answer. Now, in this case, we would have had to compute, n-1 different powers of A, or depending on how if A is given n-2 powers. There's another way we could do this. So the time to do this is going to be roughly big O n times the time to do one multiplication. Which is going to be big O n times theta n cubed, where n is the number of nodes. So what kind of algorithm is that? That's order n to the 4th. That doesn't sound very attractive, but you are trying to compute all possible connections. Now there's a way you could do slightly better than this. So let's call this one method 2. It's still related to these powers. We could instead compute, so this is still powers of A, but instead of doing this OR as a separate step, what we could do is the following. Compute I plus A. Now remember what I is, right? I is a diagonal matrix. So I is a unit matrix. It just has ones on the diagonal, zeros everywhere else. Remember that A, the adjacency matrix, nodes don't have edges to themselves. So they're going to have zeros on that diagonal. So when you add I and A together, what you're getting is it possible to go from I to J in 0 or 1 steps? So A would have been in exactly 1 step. I is in 0 steps. So I plus A, or if you want I or A, is going to be the same thing because it's ones and zeros in different places. You're going to have the meaning of those entries will be, can I get from I to J in 0 or 1 step? Now what we can do is simply raise this to the n minus 1 power, and then use the entries in there. The time to do this, of course, is what? N, take n cubed time alone just to multiply two of these. Would you think it's the same as the n to the fourth? I have to multiply this by itself n minus 1 time. Okay, that would be a naive answer. Divide and conquer. What? Yeah. What would an answer for? What's it called? Repeated squaring. Remember that? Squaring, because this is just a power. So if you just imagine, remember the algorithm for computing powers of a number. We could do that so if you can calculate b to the n in log n time, log n multiplication steps. It's exactly the same algorithm, except that multiplication in this case is going to be this funny matrix multiplication instead. And the matrix multiplication takes n cubed time. So you don't get away from that, but the number of iterations, the number of times you do it, it's not going to be order n, it's going to be log n time. So we can do this. Let me just mention that then. If we use repeated squaring, then the time to do this is going to be on the order of n cubed log n. Without doing anything too fancy on the multiplication. There is actually a slightly faster way to multiply two matrices than order n cubed. There's an algorithm called Strasson's algorithm, which uses another divide and conquer approach. But if you're curious, go look it up. All right. It can solve it instead of n cubed, it solves it in n to the log 7 base 2 time. Log 7 base 2 is slightly less than 3, so it's slightly faster than that. I understand that in practice, you need n to be really large for it to really make a difference, for you to notice the difference. All right, so those are two different methods that just use the powers, but both of them are still worse than n cubed. This one is much worse, well, a whole n factor worse. This one is slightly worse, it's only log n factor worse than n cubed. Warshall's algorithm takes n cubed time, all right? And Warshall's algorithm operates on the principle that I could just sort of gradually update my matrix by, if you think about what these are doing, each one is really saying, you know, when I do the dot products, I'm really saying if I can get to J and J can get to K, then that means that I can get to K. So in fact, what we could do is maintain a matrix that sort of has these results along the way, right? But we're not going to explicitly compute a matrix product as such. What we're going to do is essentially iterate over the entries in this matrix. The matrix that we're maintaining tells me so far, and this is, so in the kth iteration, it will tell me, so far have I been able to get from I to J. One way to think about this is, can I get from I to J going through node numbered higher than K? That's what it means. That's how you'd interpret the meaning of that.
Sure.
And so if I start iterating from K equal 1, then initially I'm saying, can I get all the entries ij? Can I get from I to J going through node numbered higher than 1? Because I'm not going through any other nodes then. So I will only have a 1 if I actually have an edge between I and J. Then what I'm going to do is when K goes to 2, now I'm asking, is there a way to get from I to j going through no node numbered higher than 2? Well, that means that I could go via 1, but that's the only thing that changed. So now what I can do is examine the matrix that I'm looking at. And if I can get to 1 and 1 can get to j, then I know that I can get to j going through via 1. But I don't have to check anything else. And then basically I just iterate and make k go 2, 3, 4, all the way up to n. By the time I get to n, I'll know, is it possible for me to get from I to j going through no node numbered higher than n? Which means, is it possible to go from I to j at all? And I would have done exactly k iterations of this. Each iteration internally would have taken me out of n squared time. Total time is going to be n cubed. The algorithm is simple enough that we can just write it up. So let's go.
Sir.
Mike. Is the camera working? Okay. Right. So this is, in fact, what I'll do is
Sir.
On the left side. So
Back
what is
up first. Yes, sir. We're in method 2 where we compute I plus a to the n. Is that n minus 1 or n plus
minus 1? Yeah. Okay. I plus a raised to the n minus 1 power.
All right. Thanks.
Okay. This is an n by n matrix. Oh. I'm gonna put, so C is gonna come in versions if you wish. I'm gonna indicate that with a superscript, but I'm gonna put it in parentheses so you don't think it's power. It's not a power. All right. So, but what that means is that entry Cij is gonna be a 1 if there is a path from I to j passing through only nodes numbered less than k and 0 otherwise. So understand that. So now the C1 of kind of doesn't matter. But do I start my numbering from 1 or 0? Okay, if I'm going to give you some Python code, then I better make it start from 0. So I'm going to say number. Yeah, that's fine. So what I'm gonna say is that C0 I'm going to initialize C0 to be the identity matrix, and then C1 is going to be C1 is going to be the adjacency matrix. I'm going to have an update rule In fact, let me just write the code at this point. Oh, well, okay, I've gone this far. So to update, it's gonna look like this. For k greater than 1, C K I J. Did I put a K on that? Let's do this. So I can make it more specific. So I'm going to say, so each entry, the ijth entry for k, or if you prefer, let's talk about the next one. So if you understand the meaning of this, then I can break this down in one or two ways. Either, because I'm asking the question, can I go from I to j, passing through only nodes numbered less than k plus 1? Yes? So the thing is that if I could get from I to j passing through nodes numbered up to k already, and now I'm investigating where I can go up to k plus 1. Huh? Yes, yes. When I say number, in other words, all the nodes have some unique number. So you have node 1, node 2, node 3, node 4, node n. Yeah, that's what I mean. So exactly, so it's just a label, right? And it's just a way of sequencing them. And so what I'm asking is, can I get arbitrarily from I to j, where I and j are two different arbitrary numbers of nodes, node I to node j, but I want to make sure I don't pass through any node numbered higher than k plus 1. All right? So the thing is, if I could get there, so now suppose I'm allowed to use k plus 1. The way I define it, they're allowed. I'll fix this later. I don't want to waste time on there's an equality edge case that I'm probably gonna screw up if I. Let me get the definition out, because it's a question of how you word it. So let me say what comes naturally, and then we'll make the text fit that rather than the other way around. So what I want to fix in your mind is that this is going to represent that I'm allowed to use nodes that, in this case, don't exceed k plus 1. So I'm allowed to use nodes that are labeled up to node k. And I want to know, can I go from I to j using nodes only numbered up to k? You understand what I'm saying? So, but what I have up until now at this point is I have a matrix that tells me whether I can go from I to j using nodes only up to k minus 1. Because that's what I have already, I would have computed Cij to k. I would have computed this entry everywhere. And now I'm trying to update the matrix to compute the next one. So obviously, if I'm allowed to use nodes numbered up to k, and I already know the answer for when you're allowed to use up to k minus 1, the only thing that changed is that now I'm allowed to use k. So if I used to be able to get from I to j using only nodes up to k minus 1, it must still be possible using nodes up to k, right? Because adding a new node as a allowed path doesn't undo the ability to get from I to j. So therefore, either I already can do this using nodes not numbered higher than k, or maybe I couldn't do it before. So maybe this is a 0. But if I could go from I to somewhere else. Now, where is that somewhere else? What is the new node I'm allowed to use? K. I wasn't allowed to use K before. Now I'm allowed to use node K. So all I need to worry about is, okay, now that I'm allowed to use node K, does K offer a way from I to get from I to J? And the only way that could happen is, could I get to K, and then could K get to J? Both paths using no node numbered higher than K. In other words, could I get from I to J, sorry, I to K, and I'm not using any node numbered higher than K, and can I get from K to J also not using any node numbered higher than K? This is I used I was using ands taking precedence over or, but I'll be explicit by putting in parentheses. Right. So how does this look in code? So that's going to be my iterations, my Ks. I would have initialized before this. You have to initialize C to be the adjacency matrix. And then you're then gonna say for, let's do rows. And then columns. And here comes the update rule now. So we have our matrix C, and then Cij is gonna be Cij or Cik, and if I use ORs, if you use ORs and ANDs, then I'm assuming I filled my matrix with booleans, right? And Cij. Brackets. So let's put the complete thing. I didn't put this. And here you return your C. That's objective. That's full algorithm. Full implementation. Let's focus in order. All right, what do you think is the running time of this? Yeah. Yeah. Sorry? So there you have it. It's possible to do transitive closure in order in cube time. That's called Warshaw's algorithm. Now, based on all this discussion, can you think how to adjust this so that you could compute all pairs' shortest paths? Suppose I kept a distance matrix so that the kth version of that matrix tells me the shortest path, the way to the shortest path from node I to J, passing through node numbered higher than K. Then by the time I'm finished, if I calculate it all the way up to the nth iteration, I'll get the shortest path from I to J passing through node numbered higher than N, which is all the nodes. Can you modify the Warshall algorithm to do this? Floyd did, yes. And I'm asking you to just be Floyd for a moment. So if you know the shortest path from I to J and it doesn't pass through K, but now you're allowed to pass through K, how do you determine whether it's better to go via K? If you go via K, you just find out what's the distance from I to K plus K to J. And if the sum of those two distances is better than going from I to J without passing through K, then you would update it. Otherwise, leave it alone. Right? So Floyd-Warshall is basically the same thing where, how do I adjust this though? What's this and get replaced by? Not or. These are not going to be distances, so this is going to be the sum. And what does this get replaced by? Min, exactly. Yeah, I'm either going to be able to get there, I could have gotten there before and it was with a lower weight, or now going via K gives me a lower weight. And then how do I initialize the matrix so it works properly? Use the, should I use my weights as if they are costs or capacities? Costs. Because I want infinity between edges that don't exist. And that way, when you add infinity here, it's not going to be the min. So if you don't have an edge, it's not gonna change your result. So we can modify Warshall's algorithm to compute the shortest path weights. Between all pairs of nodes. And what's the modification? So basically, and this algorithm is actually has its own name. This is called a Floyd-Warshall algorithm. And what's the modification? In the inner loop, or becomes min, and becomes plus. And of course, the entries in the matrix are no longer binary entries. Entries of C are now distances. Any questions? So obviously the time for this is the same, right? It's going to be the same order n cubed time. Is this better than, so when we're on Dijkstra, how do you solve single source shortest path? You're on Dijkstra's algorithm, right? Now single source shortest path is going to give us the shortest paths. You could run Dijkstra's to every node in the same run. Once you have one single source, you can just run Dijkstra's and reach and see where what the shortest path is to every other node. So that one run of Dijkstra's will tell us the shortest path from some source to every other node. But suppose I wanted every possible pair of nodes. One way is to just run Dijkstra's n times, once for each node. How long would that take? How long does Dijkstra's take? Not mn. M plus n times log n. Right. So at worst, m plus n times log n. If I do that n times, then at that point I'm now talking about mn log n. If m is really dense, so m is high, if m is bigger than n squared, remember this discussion in tutorial about dense graphs versus sparse graphs. So if m is on the order of n squared, then mn is like n cubed. And so the running time for one run, it looks like n cubed log n. and you do that n times, you just did n to the 4th log n. Not cool. All right. Even if m is sparse, mn, whoops, I confused you. The running time was n plus m times log n. My bad. So running time for one run, if m is dense, was n squared log n. Do it n times n cubed log n. I knew it wasn't so bad. N cubed log n. But this running time is n cubed. So if you have to do all the pairs, doing Floyd-Warshalls is actually better than doing n Dijkstra's. Okay? And that's the message here. Now, if you ever have to do this, just keep that in mind. If you have to do lots and lots of shortest paths, it might be worthwhile computing all pair shortest paths. Yes. Right. If you want to find all possible shortest paths, you should do Floyd-Warshall. That's the message you must take home. What I was pointing out is that Dijkstra's, pick a node to start from. Dijkstra's can give you the shortest path from that node to everywhere else in one run. Right? I mean, we discussed it in the context of a start and of a finish, and Dijkstra's tells you what the shortest path between those two is. But the only reason why we stopped there, the only reason why we only know that is because we stopped the algorithm. We halt it when we get to T. But suppose you don't run it. Suppose you don't halt it. You just make it go from start S, just touch everywhere you can reach. You would have then gotten the shortest distances to every node with the same run. But if you now needed to do it from many sources, like you don't know where you might start from anywhere in the graph, and you need to pre-compute these distances, you're better off doing all pairs, shortest paths, rather than running Dijkstra's n times. That's the message. All right. See you next week. Next week is a completely different topic, complexity theory. It's going to be relatively soft because at this level that we're introducing it, but it is important. It could be on the final. All right. You got it? All right.